Good evening. My name is Hele Kiiman, and I'm working here as a head of research. And on behalf of the Estonian Maritime Museum, I have a great honor and warm welcome to our evening seminar tonight. And maybe a couple of words about our evening seminars. Usually we hold them once a month on the second Tuesday of the month. And the topics are varying from the icebreakers up to the, Vikings, so on. So just for your information, and if you registered on our homepage, then your email, we are going to store it, so every time you will get the invitation. And as I said, today our seminar is related to our newly opened exhibition about the Venice, Queen of the Sea. And we have a very big honor to welcome our evening guest, Professor Roger Armstrong, who will invite you to think along, what can we learn from the liquid landscapes and sea environment in order to organize our life in a better way on the land. So before I introduce our moderator of the evening, let me maybe say some words about the exhibition. So if you haven't had a chance yet, I really recommend you to, in the coming days or weeks or months, to visit the exhibition, which is a story told through the display of selection of fantastic artworks from the Venetian museums. And it's curated by the major experts of Venetian history, art, architecture and culture. And as this today's evening talk, this exhibition also opens the questions or the story about the city of the Venice, its destiny, fate and fortune, which is of course linked to the sea waters and the flow around it. So let me introduce now our moderator, Mari-Liis Kell, who holds scientific degree from Tallinn University of Technology and Tartu University, and who is currently working as head of green tech of Fullscape, and where she's actually focusing on how to make a better use of the research and development in learning and to adopt the impact of the climate change. But Mari-Liis, the floor is yours, and I wish you a very nice evening and enjoy the discussions. Thank you.
Good evening, everyone, and welcome to this forum about the future of Venice. Today we have a rather exciting and I would say quite scientific evening planned for you. Our guest lecturer, Rachel Armstrong, will soon take us on a journey into the world of materials. And we will hear in about an hour-long presentation, I guess, about sea, about nature, and how we can use them as an inspiration in our architectural world. A bit about Rachel. Rachel is a professor at the University of KU Leuven in Belgium, and she's the professor of regenerative architecture. Her work is mainly related to the transition from industrial development period into a more ecological era. And her work examines how it will be possible to harness the properties of living systems and to how to upscale them and use in our built environment now. And she calls this symbiosis living architecture. She holds a first-class honors degree with 2 academic prizes from the University of Cambridge. She holds a medical degree in the University of Oxford. And she holds the PhD of architecture from the University of London. And she has written down her approaches and thoughts in numerous publications, some of which I will also mention. For example, Safest Houses, Experimental Architecture, Liquid Life, Soft Living Architecture, and Invisible Ecologies. So basically, if you hear something very interesting and get inspired, like I already have been, then you can search up these books and read even more about it. But I won't hold the floor too long now. So Rachel, you can come up and perhaps tell us how we can make a better world by getting more inspired by nature.
Thank you so much, Marilise. Oh, you can hear me because I can hear myself, so that's really great. So first of all, has anybody here been to the exhibition? Has anybody had a look around? Half of you, all of you? Okay, cool, great. And how many people have already been to Venice? Okay, most of you. Great. So I just wanted to establish baselines here, just so that I know where to start from, really. And where I want to start is by appreciating that we live on an extraordinary planet, a life-bearing planet. And essentially the cradle of life on our planet is really in the power of the sea. So as the asteroids hit the Hadean Earth, which is a liquid boiling sphere of magma, the first scant seas start to form, and then the oceans. And where the sea meets the rocks is some kind of tension. Some say it's way deep down in the abyss, and others say that it's actually at the shoreline, where strange interactions between chemistry, so iron sulfide and water, and some of the organic molecules that have come also from those asteroids now start to make this incredible brew, which is billions of years in the making. But it's quite interesting because from a barren planet to a life-bearing planet is only really maybe 500 million, maybe nearly 1 billion years. So I think life happened really quickly when it happened here. So there's something really special about the materiality of this world. And there's something really special about how the liquids and the materials interact. And whilst we may think of that and tell the story of that as happening a very, very long time ago, and that none of that is happening around here now because evolution and things change, I kind of want to introduce you into a world where we can maybe get a glimpse into those wondrous moments where things that we do not classify as life today come into existence and start to help us figure out why this might be a lively world and how our understanding of that might help us design differently, might help us imagine things differently, and ultimately might help us behave differently. So, as you are, I'm hoping that I've got the power. I might go to the mouse, power of the mouse. So, I want to introduce you to the shoreline of Venice. I'm not going to take you through the, let's say, the postcard historical images that you're probably very familiar with, or the touristy places. I'm going to take you to the very outskirts of Venice, in that space between the water and the land, between myth, between reality, between light, between matter and the sea. And Venice is in constant dialogue with its environment. Venice, like early Earth, is an unquiet space. It is not obedient. And although Venice, too, is not classically alive with DNA and membranes and a program, a metabolic program, it does actually have, as Linnaeus himself observed, some of the lively properties that might inhabit stones, for example. So stones, Linnaeus said, have a kind of life, but it's not the same life as animals, and it's not the same life as plants. But stones have a kind of participatory, strange, longer duration of change in the world. And I think this is shared very much by the landscape and the city of Venice. So I've come to think of Venice as a city as living. It is not a furry creature with two big eyes and a little nose and looks cute, but it has a life about it, I think, that is really worth looking into, because I think it will tell us how we might imagine and interact with our cities differently. So Venice, almost like a giant cell, has all these channels, liquid channels, penetrating the fabric of the city itself, coming from an archipelago initially, and then being formalized through formal building techniques, some of which are there to embrace the fact that Venice is situated on a swamp. And so the wood piles, and then ideally the Istrian marble, and followed then by more traditional building techniques, creates a water barrier between the lagoon and the formal buildings. That is a very that is a simplification of how Venice is built, because obviously starting off on marshes, its first buildings were wood. Wood becomes a fire hazard. But the city that we know, it has a strategy for sitting in water and trying to resist. You can just start to see some of the marble base on some of these brick buildings here. And with climate change, of course, with the sea level rise and with the changes in geography of the city, and with the increasing aqua alta with climate change, the level of water rising is going way beyond what was originally planned for the buildings in the city. And I think beyond the kind of conventional fabric of the city, Venice is also really well known for some atmospheric qualities, which come from this relationship with wetness, with droplets, with the sea, with the tempest, as it were. And the first of these qualities that you notice, if any, as you have been probably taking photos in Venice when you visited it, that there is something really amazing about the light. It's almost hard to put into words. You kind of have to go with your camera to the city of Venice, and particularly on a cold day when the mist rises, it starts to soften everything. The light is really kind. It is almost impossible to take a bad photo in Venice. You have to try really, really hard. And with that is the reflections then that are coming from the water itself. So not only is the light soft and diffuse because of the humidity in the air, which varies from day to day and from the different time of the day, you also get the light in conversation with reflections, and the reflections on the water and the scattering of light that you will see on the lagoon. But also, as you walk through the rios, the little tributaries that go between the buildings, you'll start to see it in conversation with the water's surface. The light sits between an underwater world that belongs to the lagoon and the sea, and above water territory that is inhabited not exclusively by humans. We all know of the pigeons of San Marco. And I'm going to show a couple of these films, one at the beginning and one at the end, really, because I think when you are using your camera and you get the aberrations from the light and the limitations of your camera, I think the images that you get from this image-making machine, this living image-making machine of surfaces, of light, of bricks, of vapor, you start to see a world that is not quiet, that doesn't fit into tidy geometries. It isn't obedient. It kind of has a quasi-recalcitrant design of its own. And I think most particularly when you catch the light coming from from any time of the day on the surface of some of these rios, the stillness becomes almost mirror-like. And from that, then, you start to get a reading of the space, that these shivering images that are never see the same image twice on the surface of the water, even if you go to exactly the same spot in exactly the same time of day, the image is almost never the same. And this generative quality of the way that Venice itself makes images, I think, really helps us think about our relationship to the elements, to the sea and water, this cradle of life, and also thinks about, asked us to think about, why do we design as we do? We like to design solid, inert geometries that are easily controlled by our hand, whereas when you kind of investigate the way that nature or the elements are inhabiting these spaces is incredibly generative. It's really revealing to us something about the potential of these spaces that is not just evident through a classical lens. And I just want to just point out, other than spending hours looking at buildings being completely transformed by the elements in which they are actually immersed, it reminds me of the techniques of Nostradamus and the scrying that was very well used at the time as a way of looking at futures. And the idea behind scrying was really a bit like a wand. Essentially, it's channeling. The magician or the soothsayer or the fortune teller that is receiving these images is collecting them from the universe, and this information comes into their body, and then they are there to interpret these signs. So the rios in that way are really channeling the elements, they're channeling the wildlife underneath, they are channeling the situatedness of the place into an image-based form. And like Nostradamus, I think that we can read these images. For example, if we want to do it scientifically, this will tell us something about the current or the light intensity. It might tell us also something about how much wind gets funneled through the space, because it's not just the water current that will make ripples on the surface of the water, but it is also the wind. So we're getting a kind of complex reading of the elements. And when I just obviously fell in love with Venice. But you can start to see that there are different worlds by paying attention to the images. On your right-hand side, you can see the image that's created by the life above the land. So that is a distorted picture of a detail of a building. And on the left, you can start to see into the canal, or the rio, where you can see the fish swimming and the algae and the green seaweeds thriving in the rio. And both of these worlds inhabit the same space together simultaneously. And often, we're not aware of both worlds at the same time. And it reminds me of Italo Calvino's book about invisible cities, where he was rereading the city of Venice through many different lenses to come up with many different kinds of places. And when you start to look at the water and the different planes of inhabiting space by different bodies when it comes to Venice, then I think we can really start to read the possibilities within the city differently. So this is just another picture, really trying to capture the interface between the man-made, the built, and the sea. And what I quite like about this picture is that it isn't a straight line. So even though when you walk along the promenades in Venice, the constructed lines are very geometric and there's a definite drop-off, but when you start to consult the water and you look at the way that the elements are, let's say, configuring space, the slippages between land and sea actually become very, very interesting indeed. And so you can put probably see the fish and the details of the buildings, you know, and how these, you can even see the different depths. So that's a much shallower piece of water. And then you've got the building in the middle, and this is a deeper part of the Rio. So step on the right, let's say, and then the body of the Rio on the left. And I think this is what really interests me when it comes to thinking about intelligence within materials, because materials can be intelligent when they're in the right context. Anything, if you treat it badly enough, or if you overheat it, or you know, kind of try to control it in a particular way, can be inert. But what's interesting is if you have a dynamic environment, then the materials respond to changing situations. You probably know from basic chemistry that, you know, in an ion in an alkaline environment will do one thing, but in another environment it does another thing. So chemistry itself, matter itself, cares about where it is. And in Venice it's quite profound, because light is one of those transforming elements that it can respond to. So is the presence and absence of water. So is the presence and absence of other minerals. So let's say matter in Venice has lots of friends and ecologies to be in conversation with. And I think also, particularly now then, when we get human-made structures, we start to create additional reflective surfaces, sun traps, you know, spaces in which matter can be concentrated in ways which is much more dilute when we're out in the sea. And I think we particularly see this, and you'll know this from, you know, from the shoreline, the encrustation. So this is actually in Venice. These are encrustations on the sides of the Rios and the canal, where you could say these are non-human cities. So what we've got here is a collection of shellfish. We have some algae. We have some bacterial mats, so they kind of look dark purple in places, or grey on this particular photo. We have bryophytes. So essentially this is mineralized, so you can see they're actually making their own kind of stone here. And so that's a kind of sedimentary process. You know, so some of it is passive, so that the sediment catches onto the surfaces of the brick structures on the wall. That provides food. The mollusks and the microbes attach. They create more geometries. They trap sediments. More creatures can attach. But also some of them are actually actively mineralizing. They have metabolisms that take carbon dioxide and calcium from the water, and they turn it into a kind of rock. So some of this rock is built by non-humans, some of it is sedimentary, but all of this is Venetian. So this is a kind of cryptic Venetian architecture, but not built by human settlers. And also we can see the beginnings of different biofilms. So these are kind of white microbial mats. Again, you know, they will take opportunities, particularly in the wooden structures that are in the water. Some of them are really deep, you know, the wood piles upholding the buildings. But some of them are more surface-based. And this is where we get the problems with the Grand Navi going through going along the side of the lagoon, because the wake sucks out the water from underneath the city, and it exposes wooden piles to air, which microbes love, and that's where you start to get rotting. So you can really see how the choreography of events in a city that isn't still really shapes the materiality of the city. And also, I don't want to give the impression that all of this is natural. Right? There's a lot of pollution in Venice, which has been brought some by industry. The minerals that I was referring to previously are coming from industry, particularly on the mainland, coming from the boats themselves, the diesel-powered engines, but also from the tourists, which you'll see the video in the exhibition of just how many tourists now come yearly into Venice. I think it was 1.8 billion on your video. And all of them get thirsty. And because you've got so many people around, people bring their own plastic bottles. And many of them end up in the lagoon. And I think every year it's something like 30,000 tons of plastic ends up in the Venetian lagoon. So it is also absolutely rich with microplastics in the sludges at the bottom of the lagoon. But again, you know, Venice is full of transformations, and it's not discriminating between things that are natural and things that are unnatural, as it is this kind of computer that really thinks through. I'll call it thinking because it's making decisions about how matter is built, particularly along the shoreline of the city, between the city and the sea. And here, does anybody know what these are? Anybody know what these are? These little nodules on the step in Venice here? No? These are thrombolites. So these are contemporary versions of like the first bacterial cities that we're certainly in the fossil record that we have. Some of them you can see at Shark Bay in Australia now. They're like little islands that are grown over many centuries by microbes, and they are like little soft biofilms. So those are the squidgy polysaccharides, the sugars and the proteins that the microbes make to attach themselves to the rock. So some of the sediments end up in that biofilm, some of it's secreted, and when the microbes die, more microbes come on top. And gradually, they build up a stone that is literally grown from microbes and sediments, some active, some non-active. And when you cut into them, you can start to see the different folds, and you can read the colors in these rocks to give you an idea, a kind of palimpsest or an archive of different minerals that have been in the space. And so here, there's a difference between a thrombolite and a stromatolite. A thrombolite is very folded, like that, like a cabbage. And a stromatolite has a bit more like a plateau. But these are little thrombolites. So here, Venice is making its own little stone knots. It's growing its own stone knots within the lagoon. So coming from a field of design, I kind of want to understand if this lively matter in a turbulent world is able to generate its own form and its own kinds of materials, its own kinds of settlements, how can we, through design and the arts, start to engage with some of the things that nature is trying to teach us about cities? So one of the first things I tried to do was to make a model. And what I didn't do was to try and go straight to computer modeling. I tried to find environments where I could relate the events that I could see that were happening at the shoreline in Venice, and try to bring them into the laboratory where I could study, for example, here, I've got gels that contain water and proteins. I can slow the water down by using a gel. I've got minerals, which mimic in some ways the contaminants that are actually in the water. And I'm using light from a light source in order to start to try to create terrains and territories. You know, how might I be able to use the laboratory environment in order to start to shape spaces? And what you can maybe start to see is that actually with the drying process and even some of the mineral changes that go on, you can start to see tiny little structures there. And that is actually cross-linking happening in the gels. And you get a rolling and buckling and folding of these materials as if it was making its own topologies and landscapes. So in some ways, there was a dynamism in these materials that was very interesting. And the question then is, so what could we do with these? In 2008, I came across this wonderful little thing. This is not alive. This is an oily droplet in a field of alkaline environment, just like a sea, really. And what you can see is that the interface, so the surface of the droplet, so that if that's an oil and the outside is alkaline, then it's going to make a soap, right? So it's making a soap, but the soap is unevenly distributed because of all the physical forces that are going on in this Petri dish. And so what you see is as the physical dynamics of the droplet and the production of soap start to interact, you start to get something that looks remarkably lifelike. But this, I can promise you, is just a little oil droplet. And just to capture that really as a sequence in time, you can just see how almost, this was the thing that brought me into this world of droplet design, as it were, which is almost like a little amniotic sac. This droplet is wriggling free from a membrane to clear the surface of its, I'm giving it motivation as well, you can see. I'm really anthropocentrizing this, and anthropomorphizing. But just, so that it gets a fresh go then at producing more substance. So this for me was absolutely amazing because I didn't think making soap could be so interesting. It's just like, whoa, soap can do this. Why didn't my mum tell me? I'd have done it, I'd been in the bath a lot more than I was. And what you're seeing here is a speeded up version of what happens then. We're going to reverse the program here. We're going to have an oil environment. We're going to put alkali in the middle, but we're going to color one side red and one side blue, and we're going to start to see what happens to that alkali droplet in a field of oil. So when that alkali has got as much food as it wants, because that's essentially what the oil is to the alkali. It's a kind of food. I'll do it again because it's probably worth seeing again. So, right, 1 drop, 2 drop. Breaks up in the middle, a bit like the washing up soap powder adverts. But what you get is some of these droplets get really madly dynamic. Not all of them. Some move very slowly, but some of them, amazing. Look at that guy. He's just... And I would expect more of them to be purple, but they're not really. They seem to possess a kind of integrity. Maybe this one's getting a little bit purple in the middle here. But all of a sudden, you've kind of got this explosion of activity that's coming from alkali and oil. Ooh, how interesting. Let's have a closer look at what's going on. So I decided to get the microscope out and see what we could do with this particular preparation. The preparation was actually developed in 1891, 1892 by a guy called Otto Büchli, who was a zoologist. And he was looking to make the first forms of artificial life. When he developed this protocol, he thought that he'd actually made an artificial organism, a single-celled organism called a protist. And so, that was what he saw. This only existed as a form of drawing at the beginning. But, I started to record it under the microscope to try and capture the interesting various forms of lively events. So this is what it looks like in better focus and closer up. So all of these I'm going to show you a whole set of little films that I took in the laboratory to try and introduce you to this idea of matter being lively, even when it's not formally alive. There's a lot of interest in biology as being an inspiration for design. And I think maybe it's the way it's taught in schools, but there's less interest in how chemistry can help us design. What's different about this kind of chemistry to the stuff that you might learn from Mendeleev's periodic table is that it's spatialized, that it has a kind of time-based element, and it's very performative. But some of my classical chemistry experiments were quite performative, but this was performative in a different way. So what you can see here is that, what's unusual about this is that if these were bubbles, so if you blow some soap bubbles, you would expect all of these to fuse into one bigger bubble, right? that's what you'd imagine, right? If you have it on the surface of a bowl of water. But weirdly, these do not fuse. It may be because the interface is still active, that the surface is still producing soap. So that although the droplets seem to be drawn towards each other, I don't know why that is. I'm not sure why they like to cluster. There's no good reason why they should. But although they are clustering, they don't fuse. It might be because there are a few soap molecules separating them. It might be to do with the physical dynamics of the droplets, but none of this is really written in stone scientifically. But what you can see is that in this environment, they gradually produce these little black dots, which are matter. And with time, that matter can be quite substantial. So the droplet will keep eating its environment until it runs out of either environment or its own body. And so in that case, then it leaves a shell, which for us would be a bar of soap, right? That's what it's leaving behind. But you can see how structured this is based on this latent, so kind of slow-moving saponification process where the interface between the droplet and the environment is allowed to find a physics, find a chemistry. And so this becomes a real source of fascination for me. I kind of want to know how the water and the oils start to interact with each other. The lighter patches have got fluorescence in them. I'm not sure I can go to the, oh, it didn't quite take off, but this one does. So you can see that you know, if I put fluorescent dye into the water, you can just see how the water is inside the droplets and you know, how these droplets retain an integrity through maybe a little soap shell, or maybe it's just the physics of the oil and water pressing against each other. But as you become kind of familiarized with repeating this experiment many times, you start to notice some things, which is it's weirdly organized. It's strangely organized. Why do these two little droplets hang out in pairs almost symmetrically over those soapy bodies? I'm sure there is a physical explanation, but you might think that this is a very rare occurrence. You'd be wrong. There are all kinds of sorts of order that come out of this basic protocol: space, time, oil, and alkali. And so here you see this like little colony of droplets kind of creating these like a floral configuration. And here we've got droplets that are a bit more advanced in terms of the production of the materials that they've produced. You can see bits are floating off here. They're breaking away as they're actively produced. And I guess these are the most extraordinary of all. I'm going to play you two of these. This is starting to play good. Okay, what are we looking at here? Okay, we've got droplets, yes. So what we've got are two populations of droplets. We've got these guys at the top, but these guys at the bottom. They've all come from the same batch. They were all born the same way out of a squirt of alkaline into an oily dish. But these two lots have grouped. Collectively, this lot has built this structure. Whoever was here has already built and abandoned their nest. You can see one little guy here hanging on to his structure. But here, look, you see that there's an attraction between the two different groups. And in that attraction, you just have to pay a little bit of attention to what happens next. You would imagine they keep on doing the same thing. They kind of don't. Just watch. There we go. What was that? I don't know. I actually can't explain it. Why do they reach some kind of tipping point in order and then reorganize themselves in terms of their trajectory? Again, one off, you might say. Okay, well, let's try these guys. Similar kind of situation. One group here has been creating these long safety structures for quite a while. These guys have escaped somewhere. There are bits of soap lying all over the place. And we've got the away team here. They weren't hanging out with these guys beforehand, but now they're trying to join in, or, you know, come and have a go if you think you're hard enough, or whatever they're doing. There is an attraction, which I think is also strange. I've done spectroscopy on this, tried to look for a factor that attracts, but I can't find anything with using my techniques. So I don't know what the attraction is. I don't know if it's physical or, you know, something else. But again, you get this kind of merging together. Something happens, there's a scuffle, and again, you get a reordering of the movement of the droplets. So that's kind of weird. I mean, these things are not alive. They may have no formal brain, no formal organizational system. And so there's something really to do with the environment in which they are placed that helps matter make decisions, as it were. This is the final one of these. I mean, you know, I love droplets, but these are the last ones I'll show you, because there's something else going on here. These have been attracted to the upper part of the film screen by alcohol. Protocells, or these droplets, love alcohol. They move very quickly towards it. And once they've moved quickly towards it, they quickly make a soap, and then they become very, very still. It's a very interesting thing that they do. So this is kind of stampede towards the source of alcohol, and then they all bunch together and they go very still. I think it's just physical. I think it's just a physical reaction, but it was very relatable. I tried to model with Autodesk what was happening in these reactions. So, you know, if you see something, you start to describe it. Let's use a bit of maths, agent-based modeling. You know, let's think of them as individual droplets. What kinds of factors might we think would come into play? And the descriptions I made did that, which look nothing like what the droplets do. However, as a way of modeling and thinking about, you know, the properties of these things, I then came across this movie, which is really interesting. So this is Stefan Raffler, and he has modified Conway's Game of Life. And what that means is that rather than thinking about a body as an object, it's an object in a context of the spaces around it. And when you start to create calculations in relationship to the spaces around it, then you start to see the kinds of patterns that are much more reminiscent of the activity that you see in the Petri dish. So I thought, for me, this was a bit of a breakthrough, because it actually says, hang on, the body is related intrinsically to the environment. Darwin, of course, says that, but we still don't design that way. This is just a little topology of the different kinds of droplets that I came across, just to give you an idea of the kinds of morphologies that were produced. And this is a formation. Some of these are rather strikingly biological in their manifestation. You know, they seem to be, you know, like worms, or, I mean, I project endlessly onto these forms. But you can, I'm not the only one, because Stefan Leduc in his 1911, The Mechanism of Life, also starts to project on these kind of osmotic forms, which seem to be reminiscent of early geometries, early kind of morphological structures. And this is the one where Martin Hanzuk developed a metabolism for this particular droplet, which, when activated by light, moves away from the light, and you can see the trail of product left in its wake. So we also know that not just alcohol, but light can also trigger chemistry when it is given a body in space. So there is a temporal kind of evolving element to these chemistries. They do change with time. This was a way of thinking about the organization. First of all, they're very, they're very fluid, and they're very liquid. They start to form, kind kind of complex arrangements, then produce product, and then form more of these encrustation-like forms along the side of the lagoon, as it were. And this is a time-based patterning. This is important for me because it shows you that when a body is in space, it's imprinting its environment. It's not neutral. It's not like I'm a little circle and nothing else is happening around it. As I'm a little circle, my little circle is changing the environment. So you think about the carbon dioxide on your breath is changing the chemistry of the atmosphere around you. The temperature of your body is changing the temperature of the space around you. So it's really a kind of a dynamic way of thinking about how matter in a dynamic form actually changes the events around it. So I started trying to figure out how we might start to design with that. So I did some simple experiments with trying to produce structures from droplets. So these were mineralization processes. And this is an example of that topology I was talking about, where you actually get a gel surface and you can start to rupture it by creating crosslinks by adding minerals. And you can also create little bodies within the space, again, if you get the right spatial ingredients and recipes. So essentially, matter in relationship to time and space really starts to take on a characteristic and a kind of forms of organization in itself. This was very interesting because literally a band of, so what you're looking at is 2 fish tanks. One fish tank on the inside, one fish tank on the outside, oil tipped around in between the 2 spaces, like double glazing. And then on the top, I added a layer of alkali. So at the top then, the alkali started to form little organizing bodies, which you can see here. But they did it in a way that looks like banding. So it was very, very regular for something that should have, maybe gone another way. But it was very interesting because the space was constrained, that the patterning within the droplet activity became very regular. And so these are some details here, and you can start to see the soap flakes forming within these bodies. You can start to see the structures and the intersections, and very much like the other protocells or the dynamic droplets that I was sharing with you, you can get a large range of different varieties. And just to think back for a second, back to what the surface of the Rio is telling us about the variation within each of the waterways, we can really start to relate to this liquid dynamism and a way of kind of activating and patterning space as a preempting some kind of event. So I started to design and engineer, kind of working more formally with geometries with Philip Beasley for a series of works called the Hylozoic ground. So Hylozoic being life-bearing. He was interested in artificial life and very soft machines as a way of thinking about more lifelike spaces. And I was interested in liquids and the liquid metabolisms and bodies. So the 2 of us came together in this kind of a more classical view of how we might position liquids in space. A learning point for me was that we could bridge the gaps between liquid bodies by the cybernetic interactions that were within this Hylozoic ground jungle, we might call it. But essentially, there are all kinds of different robot types that comprise that environment. And so the chemistries had a central feature where they were slowly absorbing carbon dioxide from the atmosphere as a way of kind of, again, patterning space. And this could be seen more directly through these Liesegang ring-based structures. Again, these are soft chemistries, gel-based, because it allows things to become organized and not dissipate with time. And so you can see that the various minerals and carbon dioxide over time actually creates the same kinds of patterns that you might see in agate and other kinds of stones. So these are ways of thinking about how do we take this liquid environment and introduce it into a more familiar form of design? How do we start to create notations to help us structure these within the environments, and how do we create different species? This is a very interesting experiment. This could be done at home. This is literally gelatine and olive oil, gelatine at the bottom, olive oil at the top. And if you take food coloring and concentrated salt, and you drop the salt, you'll see it here. You see these little, that's the salt with food coloring in it, fall and create this little strand of product. But then it becomes like a little slow release capsule, and you start to see how you can create a three-dimensional painting with these little indicator bombs. So how might that work for architecture? So what I then did was to work with Christian Kerrigan as a way of visualizing how we might start with the protocell and how we could think about how that might organize matter around the city foundation so that it created another kind of architecture. So here you've got mineralized protocells able to capture carbon, and these ones are still looking for their mineral counterpart. And the idea was that we could send them using their light aversiveness into the foundations of Venice where there is rotting wood, so they could create a mineral protective coating, like a kettle scale, around the foundations to generate something that is much more like the thrombolites, which Christian visualized in these pictures here. And also GMJ also visualized another kind of Venice then, which was using this idea of a remineralization of the stonework, but this time really using the aqua alta to redistribute the production of living rock, let's say, throughout the city. And then we created an urban map to show, strategically how we might actually be able to grow certain protective shelves around the city. So all of these, let's call them more speculative engagements with the idea of an intelligent materiality, then creates many possibilities. We kind of activate Calvino's idea that we're drawing forth these invisible cities from an original city that we all have a slightly different idea about. So can we actually be even a bit more strategic about how can we compute? How do we actually start to organize space in a way where we can encourage different events spatially? So this was a map that was made around the shoreline of Venice. So if you look over the walls towards the northeast of the city, there's actually small beaches which you can access, be careful, at certain times of the day. And in there, you can actually see the city remaking itself. It's taken the detritus and the brickwork and the glass from Murano that has fallen into the waterways, and it's being redeposited at the northeast end of the city. And so the question then becomes, with this kind of mixed substrate here, you can see there's all kinds of biological activity. We've got stone worm casts being made by lugworms, and kind of all kinds of other forms of mineralization, all kinds of other colonization. This kind of nascent city is starting to form itself. So could we maybe make some rules for how we might think of the city as an interface through which certain events are encouraged and others not so much? Well, this is Matthew Sharman Hales, who's a master's student of mine, looking at how we might actually divide up the spaces in the Rios as a kind of computational program, like the old punch cards, so spatialized, not zeros and ones, but spatialized computation, and how might we be able to organize different materials around the interface between the tidal zone and the city to start to encourage strategic growth of these mineralized and vegetal barriers, cities, however we might describe them, a different kind of living materiality for the city that's gardened rather than just imposed on the elements. And so these are some cross sections, thinking about, how do we actually start to imagine and think about the spaces that are involved. And of course, once you start to get these bioreceptive spaces that like to promote and encourage the growth of organisms, we can start to think about how we might involve other organisms and not just these little mineral droplets. This is actually done in the Black Sea. This is a very common seaweed called bryopsis. It's kind of ugly. It looks like, it's come off your hair and you threw it away. Nothing really to speak about aesthetically. However, if you take it into the laboratory and you cut it up in a Petri dish with a razor blade into little pieces, and then you cultivate it, it will grow back into a single body again. It only does it once. So it's like a terminator organism. You can cut it up, leave it alone, and then it grows back together again because it's only one cell and it can fix itself. As it fixes itself, it has what I would call a dustbin metabolism. It will eat any junk just to stay alive. And what that means is you can actually feed it iron filings, and if you put a magnetic field under that regenerating body, you can get it to grow into a magnetic shape. I wasn't expecting to do this experiment, which is why it wasn't very well designed. Photograph is pretty rubbish, but it proves the principle, which is that with these regenerating bodies, you can now start to create physical forces that allow you to think about design strategies with them. The body is still living. So then within a laboratory in Venice, the IDEA laboratory, worked with a group of collaborators. So this was Ecologic Studio. There was also Studio Swine, Julian Melchiori, just to name a few. And what we did was a big beach comb. And we took the plastics from the beach comb and started to cultivate them with algae that we took from the sides of the canal. And as we incubated them, we wanted to see if they would form like a living plastic glomerate. So we wanted to see if the algae would bind to the different kinds of plastic to form a kind of complex plastic organo material. Polystyrene was particularly good because it had little holes that would encourage algal growth in between the spaces, so it held on to a lot of water. There were also kinds of biofilms that were forming around some of the plastics, which seemed to be able to promote biocolonization. And so we came up with an idea of a new island for the city of Venice, one that removed both the eutrophication, the overgrowth of algae in the lagoon, together with the 30,000 tons of plastics that's dumped there every year, as a kind of floating new island for Venice, which is within the history of the archipelago, where there are islands in Venice that are simply made out of waste. So could we take some of these ideas and bring them into a building? Well, we made a proposal for the British Pavilion at the Venice Biennale. And the idea here was to actually bring the liquid organs of the sea and the water into the built environment space. So these are just a set of plans, really. But there are different organs. We had metabolizing organs at the entranceway, which are actually toilets, so you could pee in them, and it would produce electricity. Then you would go into the stomach, which is an amazing vegetable garden that is also bioremediating and would be able to bioremediate the polluted sediments of the lagoon. Then this is Studio Swine's rain environment, so we had indoor rain. And then around the back, we then were looking at using some of the chemistries to create electricity from the chemical interactions. And then we had an amazing space where the surface of the room could be programmed according to the light, and that was by Foster's and Partners. And so I'll just take you through so this is Foster's and Partners, and what happens was that there's nanoparticles on the surface of this environment, and so when the laser light shines on it, you can change the appearance of the light. So you can get a sunset, you can get a sunrise, and you can get a sunset on Mars because you can actually program in all the wavelengths. So this was a sunset on Mars. This was Sarah Wigglesworth bioremediating garden. These were living bricks that would produce bioelectricity. This is Studio Swine's roof rain machine, so it could rain inside as well as outside. We were going to do a water purifying tank based on Hans Rucker's purification of the Rhone water. And then this is actually from Estonia, where we'd actually taken a black mirror, which had raindrops as a computer program on the inside, and it creates ripples as its output. And it's just reflecting all its environment into the black mirror, so it kind of seems to disappear into the landscape. So these were tactics, design tactics that we learned from looking at the kinds of transformations that were possible in the materiality of Venice. This was a bit of a walkthrough as to how we would experience the space. But it really got me thinking about, when we're thinking about design, we're not just really thinking about objects. We're not even really thinking about buildings or sites. We're actually thinking about design for bioregions. How do the ecologies that are in a locale start to intersect with each other? Because they're all affected by these transformations, even if only weakly. And in this tale of a transformed Venice that I wrote, I just want to read this quote because it starts to open up possibilities for design. So at one time, it may have been enough to simply insert steel pins and plates to stop brickwork from sagging in Venice. But nowadays, the kind of maneuvers needed to shape dynamic masonry requires a knowledge of cosmetic and plastic surgery. When we combine them, we discover new ways of making windows, walls, and doors. With this technique, we can make structures appear just by squeezing out new spaces. So the idea that we can change matter through dynamic means, through programming, through applying physical forces, means that we could potentially sculpt our buildings differently. And I think I'll stop this part of the talk just by these last images. I think what's interesting about what it can learn from Venice through design is about material intelligence, the ability for materials to be able to make decisions, even in the kind of the simplest kinds of way. And then if we think about the decision-making abilities of lively matter in the right kinds of context, then we might want to think about what happens then if we bring it into contact with other kinds of intelligences. And so these are a set of renderings from AI that were taking some of the cues from the text prompts from the Living Venice or the Future Venice project, and starting to help us maybe imagine different kinds of configurations that may be possible should we be able to further these tool sets and alter our thinking to really draw forth the creativity of matter, which, as I said at the beginning, is absolutely unique to our planet. And I think that, even if the Future Venice project did nothing else but to, let's say, reintroduce the idea of wonder into the material world, I felt that that was something that was really worth exploring, and it might just help us think differently about how we imagine our living spaces and how that relates to our environments. And so I'm just going to, just love what happens at the surface of water. And again, for me, this is like a drawing of, when we design with something that is situated in a living space, that's what we're working with. That is what we're working with, not hard lines. That's the space that you emplace anything. And so I just want to really leave you with that thought. That, for me, planes, light, surface, water, bottom, all of that, yeah. And so these are a few books. And so let's say, yeah, we'll do
Do we have any questions now?
I don't think anyone controls time. Yeah, 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 yeah. Space is the only thing that we can engage with. We can't, unfortunately, we can't do anything with time. Not yet. No, not yet, not yet. You're working on something. Fantastic.
Perfect. Any other ideas, questions, or remarks?
Nanotechnology is working at a very different scale. This is something I didn't say, so thank you for that question. These are millimeter scales, so they're actually visible with the naked eye. The installation work is bigger. It's a centimeter scale. I made it slower, so it got bigger. So again, your question about time. Slow it down, it gets bigger. Speed it up, it gets smaller. So nanotechnology will be on that kind of scale. But nanotechnology is almost imagined like a machine. Rather than a transformer, which I think is what is at the heart of chemistry. But yes, it's on that spectrum, yeah.
Don't you feel that what you have shown is just showing God at work on
Sure.
any level?
Yeah, I don't think I'm any different than Nostradamus. You know, really. You know, I'm looking into this fantastic bowl that's shivering and shaking around me, and I draw something from it. You know, in 2,000 years, it may have relevance to someone somewhere, you know, or it may be very immediate, and other people may interpret it in different ways. But absolutely, yes. But I think we can't forget that part of the equation, and I think that we have made ourselves God of the design process. And I think it is very pressing and pertinent for us to, let's say, turn the world upside down again for a bit and just really appreciate, you know, the richness of the materials, the spaces, the nature, you know, that we are part of.
Do we have any other ideas, questions? I have another idea or a question. How can this research be used for actual building of a house and planning and designing this?
Exactly. Thank you for that question. So I'm actually using these principles, and I think that many of you will be familiar with the field of biodesign, which is really inviting nature to participate in the design process. A lot of biodesign is using things like microbes in a kind of mini-industrial way, where you ask them to generate polymers, so whether it's cellulose or whether that's chitin, like in the mushrooms, and then you kill them, and then you make little bricks out of them. So that's one view of biodesign, and that's better than an extractive process, because you might be reusing industrial waste. I think where this kind of thinking becomes interesting is when you're trying to design with metabolism, because this research essentially says metabolism is spatial. That's not really the image that I had of metabolism before I met Venice, let's say. Metabolism for me was more like a chemical reaction. It didn't really have a place or a context. It was kind of like a primordial equation that kind of linked things speculatively in this eternal flow of life. But once you start to see the space it opens, then you can start to think about, how do I design a space that channels the life that is there, or the air or the light that is there into a context where things can happen. And so I would say in contemporary practice, it's really about bioreactor design. So I've been working with bioreactors. Some of these bioreactors, so in the Living Architecture project, can bring together different microbial worlds that would not exist together in nature. So we can bring anaerobic organisms into contact with photosynthetic organisms. Those are two completely different universes for microbes. But if we put a membrane in between, they can start to exchange products. So that's like really amazing. We can start to rethink, let's say, circularity from the material perspective through this idea of metabolism, and we're aware of the space that we need to do that. So, in the Living Architecture project, we were really thinking about how much water a household would need in order to actually take waste, use microbes to convert that waste into electricity, clean the water, produce forms of biomass. And it's a lot more than current households currently have, because water is that medium of transformation. We need more sea in our homes. If we think about how we evolved from this, from the sea, we bring the sea inside of us, inside of cells, right? Because that's where all our nutrition is. So in the same way, for our buildings to really evolve with a circular kind of nature-based approach, we need more water in our homes and more ways of dealing with water. So it's not always a problem, eating the floorboards or, escaping into unlikely places. We need 21st century plumbing, smart plumbing that can tell you where the leak is, right? It goes, there's a leak, and you can go and do something about it, or fixes it itself. We're really behind on plumbing. We're really 19th century plumbing. We're still U-bend plumbing. And we're 1930s in terms of sewage plants. We can really do a lot better with our microbial technologies nowadays. We can get way more out of our sewage processing than we could in the 1930s. So if we can incorporate these things into our houses, then, so for me, there are two ways that these dynamic materials or dynamic exchanges can work. One is in the production of new materials, so mycelium biocomposites, microbial celluloses, all those kinds of materials. And then the other one is kind of metabolic processing, bioreactors, to take away the systems dependency on fossil fuels. So, fossil fuels are only microbes that are very old and put under a lot of pressure. And before they were put under a lot of pressure and died, they had incredibly rich metabolisms, which produced a lot of different kinds of compounds. So can we actually activate that metabolic space and design appropriately, watching how matter actually works, rather than prejudging where we think it should be working? So that's what this work was telling me.
And I guess but I guess we do need a sort of a shift in thinking anyways. We have the very huge goals in Europe and also in Estonia that we have to reach with the Green Deal and trying to implement circular economy. So I guess this could be also actually practiced here in Estonia.
I absolutely think so. If we think about again, I like to go back way in time, because I think we have a lot to learn from our ancestors. and not just our human ancestors, our microbial ancestors, because they are the ones who has kept life ticking over on this planet for 3.5 billion years or so. So we have a lot to learn from them, because in a very short space of comparative time, we've done a lot of damage. These guys, they made biodiversity. They made an oxygen-rich planet. They made rocks. They made all kinds of stuff, that we have just reaped the benefits from. So if we go back to microbes, just think of that for a moment. Can we rethink a relationship with the base of the biosphere? That's what they represent, the living base of the biosphere, to transform how we work. And so I've been working with Helle and Marelise to rethink maybe some of these ideas about circularity and green economy through microbial processes. And so what we're doing is really thinking about what are the new types of building in the 21st century. What is an ecological building as opposed to an industrial building? And so where we started off was obviously the toilet, so that where what we consider waste can be transformed into a whole range of other things through the actions of microbes. And so we made a speculative design for here, based on the what we want is a toilet that isn't just something that you stick under the stairs, that you really don't want people seeing, or it's squeaky, white, and clean because you want to be seen to have a certain kind of antimicrobial hygiene. But we really wanted a space where, of course, we have a good relationship with microbes, with microbiomes, that, you know, people can touch things, but yet it's attractive, and also is an attractive kind of type of building. But so we started off with the idea of the toilet, and this one, because it's based on anaerobic microbes, we can use microbial fuel cells which generate electricity. So this toilet can provide electricity for street lighting, or to charge a mobile phone, or you can play computer games on it. Probably don't do it whilst you're on the computer. Anyway, but so you can actually use this electricity in many different ways. It also gives you a clue that in microbial fuel cells, probably the optimum voltage that you'll get out of a microbial fuel cell stack, and we're going to be working hopefully with 1,000 units in order to generate this kind of power. But we think that 12 volts is about right. If we think of how we extract energy, if we work with living processes, then 12 volts is about right. So that then gives us a clue about our lifestyles. We should not be using appliances that require 230 volts. It's just not sustainable. It's also not natural. You know, this is chemical. It may be lightning and thunderbolts like Frankenstein, but nature itself generates electricity. The muds generate electricity. Soils generate electricity, but it's highly distributed. And so if we can capture a 12-volt lifestyle within a home, it tells us what we need to rethink. Refrigeration. Maybe we should look at some smart materials to do some of the refrigeration process. You know, when you stretch them, they become cold. When you press them, they get hot. We have this kind of knowledge. We've just got into certain kinds of ways of doing things that we assume is some kind of universal norm, but it's not true. So I think that if we can rethink, even in the next 20 years, a 12-volt lifestyle, that doesn't mean that you have to do without. It means you do some things differently, not all of them. But now we've got electronics that are requiring much, much less than a 12-volt supply. You know, only a couple of volts in some cases. So we're actually getting an advanced electronics that doesn't require 230 volts and all the losses that go with that. So I think when we look at these metabolic processes, we're actually getting clues about how to live well in the 21st century at a time of climate change and a time of biodiversity loss, that we work within the resource capacities of a living system. And I think this is where some of these explorations are really coming in. These are real project proposals. We did actually just get funding for this one, which is hydroponics that uses the muck from, you know, your sink or the toilet to produce natural phosphorus and nitrogen and carbon sources. It's a no-brainer. It should already be happening, but it hasn't happened because we are wedded to the idea that nitrogen comes as a chemical that's very similar to TNT, you know, dynamite, you know. So, you know, why not use natural sources of nitrogen rather than letting them all go out into our rivers to create eutrophication and ecosystem imbalance? So if we can actually use our toilet wastes to grow vegetables, you know, and we have filtered, there's a processing tank on top, we can actually use hydroponic systems. We could have this as a kitchen. We have an arts partner who can also work with robots that will be in conversation with plants, but that's another level of intelligence. But very basically, you could have a whole bunch of plumbing in your kitchen from which you could literally have green walls, and you'd need almost, you know, no septic tank. You know, and anything that you did discard would already be well processed to be healthy for the soils and environment. So these things are possible if we rethink them. This is a bit more artsy. We were trying to think about if we wanted to incorporate this into a bathroom or a kitchen, we actually need to make these geometries look interesting, that the complex flows of water, or let's say the inner seas of these spaces, need to go through structures that are attractive and livable and have affordances that maybe we don't have right now. So this is another design for how these microbial fuel cells might start to look. And just to give you an idea of what they look like right now, these little boxes are microbial fuel cells. I think you'll be able to see them slightly better. But essentially, just fed on muck. This is artificial urine because art galleries have issues with health and safety if you use real urine. But if you peed in those, you would keep this light going on. The video behind it is actually data coming from those microbes, animated as an installation. And you can just about see into the tops of the boxes these little rolls of membrane with electrodes in it. And literally, they are harvesting your pee for electricity. And so it's useful energy. There's been, because the microbial fuel cell was invented in 1911, there is a prejudice against microbial fuel cells in that they've been around a long time, so therefore they don't work. Actually, it's only really the turn of this century with Bill Gates' interest in reinventing the toilet that actually investment went into these kinds of technologies that had previously been neglected. So they're now kind of reaching an efficiency that will be comparable with some kinds of solar panels. Not everything, we're not there yet, but this is an emerging technology that with further investments like with the hydroponics, will be able to increase the efficiencies and make them portable. So that means next time you're stuck up a mountain, your cell phone's flat, you've got no Wi-Fi. Actually, your pee could save your life because we can now use microbial fuel cells to charge up a 6G Wi-Fi system and also charge up your phone. So, if all the lights are out, the floods come, there's a blackout, you can still call for help as long as you can pee.
Amazing. Well, coming back a bit to Venice, well, in the situation that where we have the climate change and sea level is rising, then again, I guess we should go back to the old knowledges and old ways and using microbes to maybe even build cities into the sea again, like Venice in the old days.
I think it would be really interesting to see how we can garden. I think they call it the blue zone. I think Australia has got one of those around a part of the coast in Sydney, that actually you can cultivate blue zones around cities that actively invite microbes. And I don't know if you guys are aware of this idea of bioreceptivity. Bioreceptivity is an idea of patterning surfaces. It's very popular in concrete at the moment because concrete is so bad for the environment. But if you texture surfaces, it invites colonization. You'll see it on any old building around the city. It looks like a little dark patch or a green patch or a yellow patch. And this is just microbes going, hey, there's some water here. We're going to hang out. We like this space. It's a natural process of succession. But modernity asks us to scrub this stuff off because it's not sterile. But that's exactly what the world does. That's what nature wants. Nature wants these cryptogamic crusts, which are our new soils. So we're killing our early urban soils by having our buildings too clean. And if we texture our surfaces with bioreceptive details, and what that means is you need an irrigation system that collects moisture from the atmosphere, whether that's rainwater or whether it is just cloud and heavy condensation, and channels it slowly onto the surface of a material. And what happens then is that your very early plants without roots love this stuff. Microalgae, bryophytes, all these kinds of little rootless organisms. They don't damage the brickwork. Mosses are another one. They'll just stick to the brickwork and they'll create another insulating layer that absorb most of the water. And they absorb carbon dioxide like better than trees. And they also remove nitrogen, so from the car exhausts, once that nitrous oxide goes into the water, these plants are fixing all of that. So I think, in some ways, we could, if we reconfigure what our idea of aesthetics is, and be nice to nature, make spaces for nature through bioreceptivity, I think we can really start to make inroads into some of these big challenges that we face. Yeah. Yeah. Yeah.
Some 100, 150
Yeah.
and more years ago,
Yeah.
because it obtained such a kind of a very thin layer of moss,
Yeah.
gray moss.
Yeah.
And here buildings were not like in Sweden where they are red,
Yeah.
or Norway where they are white, They didn't color
Okay.
them at all. And this layer of gray, it
instead of actual paint. Yes. Yes.
Oh, wonderful. No, beautiful. Yeah, I'd love to go and see it. Yeah, brilliant. Fantastic. Inspiring.
It's another example of we don't always need
It's not necessarily new. I mean, your question was about, isn't this just what God does? Yes? Totally.
Do we have any other questions?
I absolutely agree. Yeah. Exactly, we're losing that knowledge. Yeah, we're losing that knowledge. I'm afraid, because we have a preferred aesthetic, which is the machine aesthetic of Corbusier. So everything is sterile, everything is clean, everything's nice and bright and shiny, and got hard surfaces. But I think some of these softer kind of more inviting, I think, geometries and textures, really, we need the artisanry to bring that back, because when we mass manufacture stuff, it is easy to do something with a sheer surface. But when we make stuff, we pattern it with our skill, right? We can create these kinds of details, and the pattern went out with high modernity. I think is a real shame. So yeah, absolutely. Craft, I think, is really also at the heart of this. This isn't just about one company making a solution for everybody. It's about re-engaging with materiality, craft, and nature. And I think that, as you say, absolutely at the heart of the 21st century now.
So if you would plan your own building, like you get the chance to create the kind of building you would want to have yourself, what would that building be like? Would that building use the similar kind of protection layers?
I think you've just described it, yeah. So it's not about kind of, tearing everything down. I think it is about this layering. If we can replace fossil fuel-based systems with, at least some bioreactors, even if they're outside, we don't have to have them, under the bath or it's about thinking smart through design. And I think if we can think of natural alternatives to some of the things that we need, then we should really be doing that. And kind of bringing that knowledge back into the commons, back into education, back into, design education. I think that is really critical at this time.
Okay. Any other thoughts? No? Yes.
You must be hungry.
I have only one more question. Last one, I promise.
Okay, yeah.
You went to see the exhibition.
Yeah.
Tell us what you thought and what you took
You know
from
what?
that.
I'm a sucker for Venice, and I absolutely love the display of cultural heritage. I really relate to the kind of the magnificent Venice, let's say, that Ruskin fell in love with. So all of that was absolutely wonderful. But the cherry on the icing on the cake that is an exhibition in Venice was the children's area. Oh my God, I was so there. That is so interactive. Whoever designed that needs an Oscar or something. It is just beautiful to be able to step into a world that really feels like you've arrived in the place and it's not a museum exhibit. So for me, kids' playground, making masks, seeing the little animations on the screen. Oh my God, that was just genius. Yeah, fantastic. What a fantastic exhibit you have.
Fantastic. But thank you so much. It was truly amazing and inspiring.
Okay, thank you very much. Thank you for spending your evening with me. Thank you.